Today's our topic is principal stresses. Now, what actually is principal stress or principal plane? We will also find out the uh, the stresses on an oblique section and its derivation. That is very quite important in for civil commission paper, in diploma papers, in final papers of engineering studies, civil engineering studies. Principal plane. Initially, what is principal plane? Principal plane is a plane is a point where there is no shear stress. Okay, it has been observed that at any point in a strained material, now this word strained material means a body in isn't. For example, this is a body, and this is in stress. Okay, compressive stress or tensile stress. Now this body will go through under a change in length, and this change in length is known as strain, or we denote it like this. So any body under stress is known as strained material. Okay, now I can say that it has been observed that at any point in a strained material there are three planes mutually perpendicular to each other which carry direct stresses only. Direct means I can say that perpendicular stresses. Okay, so for example, this is our body, and this is a point where there are direct stresses. So it means that there are three mutually perpendicular planes: x-axis, y-axis, z-axis, and these planes, if these planes are under zero shear stress, then we can say that these are principal planes. Okay, now the stresses that are applied on this principal plane, for example, this is stress, direct stress 1. You can draw it 1. The direct stress 1, direct stress 2, or direct stress 3 applying on these planes. Then these are these direct stresses. Then the direct stresses are called as principal stress. So the stresses applied on principal planes are called principal stresses. Okay, this was the complete concept of principal plane and principal stresses. Now there are methods for the stresses on an oblique section. Now we knew, if you don't knew about this little thing, that within a soil, for example, this is our this is a land sliding. Okay, and we know that whenever landsliding occurs, it occurs at a plane like this. So for example, there is a body. Now the failure usually occurs at an angle, in an oblique section. So we need to find out the stresses in an oblique section. So to find out the stresses in an oblique section, there are two methods. One is analytical, another is graphical. Graphical method is well known, all of you, that Moore circuit. You all knew what both of these methods will be covered in this lecture series. Now initially we will study analytical method. So in analytical methods and in graphical methods, in both methods there are total of 5 cases, but in analytical method we are only going to learn one case, because other case will be get self-explanation by this one case. Now for example, the case we are going to encounter or study is this. For example, it is a body, this is an oblique section at an angle theta. We need to find out the stresses here. Stresses means direct stress and normal stress and shear stress. Usually direct stress is shown by this n, small n, and shear stress is shown by this sign, tau, usually known as tau. Now I told you there are a total of 5 cases. So in case 1, in the case we are going to encounter or study is this case in which 2 direct stresses and 1 shear stress is applied on a body. Okay, this case we are going to study in this lecture. Other cases are self-explanatory. In the second case, only 1 direct stress is applied. So this one case. First case is this. In second case, 2 mutually perpendicular forces are applied in this way, and we need to find out the normal stress and shear stress in an oblique section. In third case, we are only given 1 shear stress and no direct stress, and this shear stress we can denote like this. This shear stress is for example, this is my body, and this is shear stress. In third case, we are only given shear stress. We need to find out normal stress as well as shear stress in an oblique section. Oblique section is this at theta. Okay. In fourth case, we are given a shear stress and a direct stress. In fifth case, we are given this, and in this fifth case we are going to study or derivate. It is quite important with respect to engineering studies and final exams. The question comes about this topic, or in diploma as well, and commission paper as well. So for example, we have a statement. Now initially ignore this figure. Okay, we will make this figure using this statement. Now we are going to find out stresses on an oblique section. Okay, oblique section is, for example, this is a body, and oblique section will be like this. Okay, so we are going to find out the stresses in an oblique section when subjected to direct stresses in 2 mutually perpendicular direction. Subjected to direct stresses in 2 mutually perpendicular direction. This means one direction and mutually perpendicular this direction. Okay, and these both are, we are assuming that these both are tensile. We usually take tensile as positive. Accompanied by simple shear stress. So we are providing the shear stress in clockwise direction. Okay, so we are also assuming that this angle, oblique section, is angle of theta with respect to major tensile stress. Okay, now what is meant by major tensile stress? Now we are giving this as stress x and this stress name as stress y, and the shear stress as txy. Okay, now you need to understand major tensile stress, angle from major tensile stress, angle from major principal plane. Now we are also assuming that stress x is greater than stress y. Okay, so before coming to this, I was supposed to give you a bit of concept here, that we knew that in principle there are three mutually perpendicular planes in principal planes. Okay, so the stress applied on the principal plane is called principal stress. Now definitely at one point there are three mutually perpendicular planes. It means there will be three direct stresses. One will be on one plane, other will be on the y-axis plane, and another will be on z plane. So it is said that either of these stresses, one will be maximum, one will be minimum, and one will be in between these two. And this is a simple concept, the simple property of a real number, that the relation, there must be two relations, either of three relation between two numbers, that either two numbers are equal, greater, or smaller. So the concept works here as well. There are three stresses, one will be major, other will be minimum, and one will be in the intermediate plane. So this was concept I forget to give you. Now coming back towards our derivation. Now where were we? I was about to tell you about this angle. I told you that this angle is theta, and this angle is from major principal stress. Now either of these two stresses, stress x and stress y, one will be major. I am assuming that my stress x is maximum, major, means my major stress here is stress x. So I told you that my angle theta is from major principal stress. So major principal stress is this, with a different color. Major principal stress is this. So this is my stress. Okay, so my oblique section will be at an angle theta from this plane. Okay, this was major principal stress. And if it is revealed that the angle is from major principal plane, now my stress is this. Okay, now my stress is this, but what is the plane of this major principal stress? This is the plane of major principal stress, this. Okay, so if it is said that the angle is from major principal plane, now my angle will be like this. Oblique section will be at angle theta from major principal plane. Now plane is the whole surface from where the major principal stress is applied. Okay, now this is the major, about major principal stress and this is major principal stress angle and major principal plane angle. Now if it is said that the angle is from minimum principal stress, then definitely I will talking about this, and the angle will be from vertical. Okay, either vertical or where I will put this force, and minimum principal plane will be this one. This was a little bit of concept. Now I have my figure. I understood already this my oblique section will be at an angle theta from major principal stress, and my major principal stress is here, stress x, and shear stress is in clockwise direction. and here minimum principal stress y. Now remember that if one side of an object is subjected to uh, a shear force in clockwise direction, the other will be in anti-clockwise direction. Now this is a simple concept, a concept to cram. So if my this side is subjected to clockwise, my this side will be subjected to anti-clockwise shear stress with same magnitude to counterbalance it, and this side will also be in the opposite direction to counterbalance it. And this is the figure. Okay, now coming towards, this is how I made a figure. Now I will derivate a formula for my major principal stresses. Before major principal stresses, I will write the formula for maximum direct stress and shear stress is here. I will once again reveal that direct is normal stress and shear stress initially. After finding this normal stress and shear stress, I will find out maximum principal plane, maximum principal stresses and maximum principal planes as well. Now I will initially break these stresses into forces. How? For example, look at this figure. These all are stresses. Initially I will break all these stresses in forces. Now you can actually see this figure, don't need to ignore, because I have made this figure using this. For example, I only don't have given names, so using this figure I am going to draw a triangle of an oblique section. Now I knew that this is my oblique section. Okay, at angle theta I am naming as A, B, C. You can give your own name, no problem. Now what we need to find: normal and shear stress. Okay, now I am not making these normal or shear stress. Now make it like this. Okay, now coming towards this side, I knew from bottom I am the body is subjected to anti-clockwise shear stress, and in this direction it is in clockwise shear stress, and direct shear stress and tensile force, and direct shear stress of tensile, it's an stress y, stress x, and shear stresses xy, shear stress xy. Okay, now I'm breaking these in all in forces. For example, I'm naming P1 to stress x. Now I knew that stress is equal to force per unit area, so to find out force I will just multiply stress into area. Now I am naming my stress x in force as P1, so stress x will multiply with its area, then I will get my force P1. So stress x multiplied by its area will be this. Okay, this is shown as AC in pink color, so I can give that AC. Okay, so my P1 is equal to stress section to AC. Likewise, I am naming my P2 with a different color. P2 is also equal to stress TX Y into AC. Now definitely this area will also contains thickness. I'm assuming that my thickness is just 1 unit, so I don't need to multiply it with thickness. I can mention here that there is a just unit thickness. For my P3 it will be stress Y multiply by, well, you got understood this concept, I don't need to do, but still it will be CB. Okay, and for my P4 actually P4 is equal to stress XY and CB. Okay, so initially I have to convert these all into before that I also need to convert stress N is equal to PNO. It will be PN, means force PN is equal to stress N into AB, and shear stress will be equal to, or shear force actually, shear force will be equal to tau AB. So I have resolved all these into forces. Now what will I do? I will redraw the figure. For example, I am redrawing the figure here. Okay, now I knew this is my A, using A, B and C. A, this is my B and this is C. Okay, now I will resolve all these the forces that I showed in the above figure into normal and shear stress. For example, this is my normal stress N and this is my shear stress, or even I can show shear stress just along this line. Okay, so by shear stress not, I have to mention here forces only. This will work because this makes a bit of, so now I am going to these are my forces, and PN and PT. Okay, normal force and shear force. Now I have total of 4 forces, 2 shear stress and 2 normal stress. Now I will break all these in normal and shear components, normal components and shear components. Now one thing, all these forces that I apply, for example this force, this force, this force and this force, all of these forces will have components in P as well as components in shear. So I know that, for example, for one force, for example, this one force definitely have the components in x-axis and in y-axis like this, and one will, to find out the component 1, I know that, for example, this is p, so that my x component px will be p cos theta if this is theta, and the py component will be p sin theta. So all I or we need to find out is to find out that which force have which component in normal and which component in shear. So definitely there are two components. Okay, so either the component will be in normal or shear. One will be in sin theta, other will be in cos theta. So the first thing we need to find out is the angle the force is making with either with normal or with shear. If the force is making the angle with normal, then the component p cos theta will be with normal, in normal, and the other with sin theta will be in shear. Likewise, we will break all these four components in normal and shear forces. The other thing we need to find out is the sign. Now we are free to give any type of sign, but initially we need to mention which type of sign we are going to give. I will solve this question and this will elaborate you a lot. For example, my first component I am taking as this shear stress. I will darker pen, wait a second. For example, this is my stress n. Okay, now initially I need to find out it is making angle of theta with normal or shear. For example, this is my, it is acting in horizontal direction, so this is horizontal direction. Okay, now I knew that through the formula, through the rules of trigonometry, the adjacent angle means this angle will be same as this angle. Okay, so this force is making angle of theta, wait, not this, but actually this will be adjacent angle, this will be theta. Okay, so my shear will be in cos, so my angle is with shear. Okay, I will mark it as theta. This is my theta, and I find out that this angle is also theta, so my shear component will be Pn. Wait a second, it's Pn. Okay, so P1, oh, I have already mentioned that it is P1, so my P1 will be in cos theta in shear, theta and normal, P1 sin theta. Now this first force P1, I am making the direction of this P1 as positives, and the other sides will be negative. To get a more concept of this, for example, this is my force. Okay, now this is at this plane, now this is the plane, now its shear component will be in this direction. No, perpendicular component will be in this direction and shear component will be in this direction. Okay, so I'm making my sign convection as, for example, this is my plane, so direction in this and this is positive and other this one and in this direction is negative. Okay, these are my sign conventions. I drew this sign convention with respect to my first force P1. Okay, so these both will be positive. Okay, now the second force, it will be P2, and my P2 will be clockwise in this direction, P2. So first thing is to find out the angle theta. For example, I'm shifting this forces here in here. Okay, now I knew that this and this line both are perpendicular, and this line are perpendicular. Therefore, the angle of theta between this line and I will clear a bit. For example, if we have four lines, for example A, B, C, D. If A and B are perpendicular, C and D are perpendicular, then the angle between A and C will be equal to angle between B and D. It is clear? So in this case, for example, now this is my force. I am supposing my force is here. So if this line is perpendicular to this line and this line is perpendicular to this line, so the angle between this line and this line will be equal to angle between this line and this line. So therefore my angle will be theta. So the P2 is making angle of normal with normal. So as the angle is normal, so my normal component will be in cos. My normal component will be in cos. So it will be P2 cos theta, and this will be P2 sine theta. And about sine, I knew that, for example, it is applied here, the force is applied in the opposite direction, this. So my normal component will be in this direction and shear will be in this. So according to this, my normal is this means negative and shear is this means positive. Normal is negative, shear is positive. Normal is negative, shear is positive. Normal is negative and shear is positive. Okay, now like I have solved both of these, you need to find out more P3 and P4. Now I will just directly put these values and you are supposed to check out that I have actually solved in the right way or in the wrong way. Means for me P3 normal is positive and P3 cos theta minus P4 sin theta. Find out yourself and check out and mention if the answer is incorrect. Okay, P3 sin theta minus P4 cos theta minus P4 cos theta. So this is my normal and shear stress. Okay, and now after finding this, I am just finding normal stress. So we have resolved the forces and components in normal and shear stress. Now we are going to find out the formula for normal stress. So for this we are going to find out the formula for normal stress. Normal stress. So from the previous formula, if I put all the values of force, means P1, P2, P3, P4, this I have already derived here, these values, then I will get this formula. Pn means normal force is equal to P1 into sine theta, or I can, with P1, in place of P1 I can put stress X, AC sine theta, AC sine theta, minus stress XY, in place of P2 AC cos theta, and much more like stress Y plus stress Y BC cos theta, BC cos theta, minus stress XY BC sine theta. These all are segments, okay, we don't know their lengths, and it should be further. Now I knew that stress N Pn is equal to stress N divided by AB, so I can write this as stress N is equal to Pn over AB, or this whole formula divided by AB. Okay, now for first stress X, AB sine theta, AB AC sine theta, AC sine theta divided by AB. Likewise minus dot 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 means all of these divided by AB. Okay, now using this small triangle, for example, I knew that my triangle is wait, it's not working. I knew that my triangle is this. Okay, this is A, B, and this is C. So using this, and this is theta. Okay, now I will replace AB. Now I knew that for sine theta, my will be sine theta will be equal to perpendicular, means this perpendicular upon hypotenuse, means AC over AB. Sine theta is equal to AC over AB, and cos theta will be equal to base upon hypotenuse means CB over AB. So from here I got my AB is equal to AC over sine theta, and from here AB is equal to CB over cos theta. Now using these, for example, this formula and this formula. So for example, this whole is divided by AB. Okay, AB. Now I will put AB either this or either this, depending upon either I have AC or BC. To cancel this AC, I will put AB is equal to this. To cancel this BC, I will put AB is equal to this. So after AB means, as AB is always here, so after dividing this, I got my formula. I got my normal stress is equal to stress x sine square theta. Stress x sine square theta minus shear stress xy sine theta cos theta sine theta cos theta, and plus stress y cos square theta minus stress xy is equal sine theta cos theta. Okay, now these both are same, so these will add and I will get this formula, and I got I will solve this. I knew that sine square theta is equal to 1 minus cos 2 theta is equal to 1 minus cos 2 theta, and I wrote that cos square theta is equal to 1 plus, and I knew that cos square theta is equal to 1 plus cos 2 theta, and I will add both of these, and I knew that sine theta and cos theta is equal to, wait, I will just write these values here. So my normal stress means stress N is equal to stress x by 2 because these all are divided by 2. Okay, so stress x by 2 1 minus cos 2 theta plus stress y by 2 1 plus cos 2 theta minus 2 times t xy sine theta and cos theta. I can directly write as, because I know 2 sine theta cos theta is equal to sine 2 theta, so I can write that it as well. T xy is equal to xy sine 2 theta sine 2 theta. Okay, as I know sine 2 theta is equal to sine theta cos theta. So solving this more, I knew that this vector, now this will be multiplied with this and this will be multiplied with this and this. So I get my final answer is equal to stress x plus y stress y whole upon 2, okay, minus stress x minus stress y whole divided by 2 cos 2 theta minus tau x y sine 2 theta. Now the way I have solved this normal stress, in the same way shear stress will be solved. Shear stress is here, okay. In the same way I have solved normal stress, in the same way shear stress will be solved. Now after, for example, we have solved the shear stress as well, we find out that our shear stress means this is equal to stress x minus stress y whole divided by 2 sine 2 theta minus tau x y cos 2 theta. So this is the answer. This is the derivation for shear. Now as we have find out in an oblique section, for example, this is our oblique section, and we have find out the normal and shear stress. Now it's time to find out phi. What is phi? It is the major principal plane, means we will find out the angle of major principal plane, okay, and we will find out the stress 1 and stress 2, or we can say the stress maximum or stress minimum, means the stresses on major principal plane and minor principal plane, means major principal stress and minor principal stress. So to find out